Imagine, if you will, a time and space where you're going to do a lab called Beer's Law, and it's going to have nothing to do with beer. Be prepared to enter the chemistry zone. In our darkness, it would help if we had a flashlight. Everybody has used a flashlight before. Flashlights put off light with a given intensity. Intensity is a quantity of light. It's a measure of how many lights there are. The classic unit for measuring intensity is a lumen, which is equal to one candle, basically. So the more intensity would be like the more candles you had giving off light. So we have a flashlight, and that flashlight's shining some light. In front of that flashlight, we put a piece of paper. What do you think the intensity is going to be on the other side of the piece of paper compared to the intensity before the piece of paper? Well, you can try this experiment at home if you want to, but it's pretty obvious that the intensity of light is going to be, the intensity of light after the piece of paper is going to be less than the intensity of light before the sheet of paper. The paper is going to absorb some of the light or reflect it. Going to prevent it from reaching the detector. In this experiment, what's our detector? Our eye over here. All right, we can repeat this experiment, this time in front of our flashlight. We're going to put not one piece of paper, but 2 sheets of paper. What do you think the intensity is of the light passing through the paper now? It's going to be even less than the intensity passing through 1 sheet of paper. 2 sheets of paper is going to absorb more, correct? Common sense here, yes? So our intensity leaving the flashlight is going to be greater than the intensity when you have 1 sheet of paper, when the light passes through 1 sheet of paper, and the intensity of light passing through 1 sheet of paper would be greater than the intensity of light passing through 2 sheets of paper. Oh, but let's go wild. Let's go all in. Let's take our flashlight and place not 1, not 2, but 3 sheets of paper in front of it. How much light's going to be passing through our paper now? Even less, right? The more sheets of paper, the less light passes through our paper. Less light passes through. So we could correctly say that as our number of papers, as the number of sheets of paper increases, the intensity of light passing through decreases. Can we say something absolute about that? We could if we expressed it as a ratio. We could say that as the number of sheets of paper increases, the fraction of light passing through, the fraction of the light passing through our sheets compared to the fraction of our initial amount of light passing through our paper is going to decrease. Common sense, right? Chemistry is easy, life is hard. And you're right, it is. And the point of this is, if you'd been alive 100 years ago, you could have become rich and famous for discovering this very obvious fact. Because that's what Beer's law is telling us. Beer's law is saying, instead of concentration, it's using, instead of paper, it's using concentration. Beer's law is saying that as concentration increases, the percentage of light passing through a sample, or the fraction of light rather passing through a sample, the fraction of light passing through our sample decreases. As concentration increases, the fraction of light passing through decreases. We refer to the fraction of light passing through our sample as percent transmittance. So percent transmittance is the intensity of light after the sample divided by the intensity of light before the sample times 100. Why don't you write down vodka? Write down vodka. Write down vodka. I said write it down, not drink it. Write it down. Vodka. Percent transmittance is inversely related to concentration. Now, as chemists, do we like inverse relationships? No. We like direct ones. Therefore, we're going to play with percent transmittance just a little bit to turn it into a quantity known as absorbance. Absorbance is a measure of the light absorbed by the sample. With percent transmittance, we are looking at the amount of light that passed through the sample. With absorbance, we're looking at the opposite trend. We're looking at the amount absorbed by the sample. So what do you think the relationship is between absorbance and transmittance? Well, whoops, first of all, absorbance is represented by a capital letter A. So what do you think the relationship is between absorbance and transmittance? It's an inverse one. The higher the absorbance, the lower the percent transmittance, and vice versa. The higher the amount of light making it through the sample, the less the amount absorbed. So they're inversely related. Now, mathematically, absorbance is equal to the log of 100 divided by the percent transmittance. If we were to put it in terms of our flashlight demonstration, we would say that absorbance is equal to the log of our initial intensity divided by the amount of light passed through, the multiplicative inverse of our transmittance. Absorbance has values ranging from 0 to 2. 0 absorbance corresponds with, we do it in a different color. 0 absorbance corresponds with 100% transmittance, right? If you absorb 100%, if you transmit 100%, your sample absorbs nothing, then you'd expect absorbance to be 0. At an absorbance of 2, however, your percent transmittance is 0. Your sample has absorbed none of your light has passed through your sample. Your sample's absorbed all of it. Alright, so it's pretty obvious that absorbance and transmittance are inversely related. Now, we said that transmittance and concentration are sheets of paper. We're also inversely related. So, therefore, what must the relationship be between absorbance and concentration? Well, when absorbance increases, percent transmittance decreases. And when percent transmittance decreases, it's due to an increase in concentration. Therefore, absorbance and concentration must be directly related. It turns out that that is indeed the case, that if you plot absorbance versus concentration, you get a graph that looks I'm going to blow it up here. We have absorbance on one axis, concentration on the other. You get a point where you're perfectly linear, and then it kind of levels off. But you have, in that absorbance concentration, a large linear portion. The formula for that linear portion of your graph is absorbance equals the slope times concentration. A chemist known as Beer, hence Beer's law, took a look at this graph and found something else very interesting. He actually quantified what was causing this slope. He further defined the slope. It turns out that slope here in your Beer's law formula, is equal to path length times something known as absorptivity. Your B is your path length, and your funky epsilon with a little hat there is a factor known as absorptivity. Real quickly, let's talk about what this better yet, before we talk about what absorptivity is, let's summarize here. Beer's law is formally written as absorbance equals path length times absorptivity times concentration. Graphically, we would view Beer's law as absorbance equals the slope times concentration. If we were to examine our two new friends here that we've not met before, path length and absorptivity, let's take them one at a time. First, let's take path length. It makes sense that if you have a substance here that absorbs light, which of these two do you think is going to absorb the more light? Where the light has to travel through a large portion of the substance or through just a small portion of the substance? The one where it has to travel through a large portion of the substance is going to absorb more. Therefore, how far the light has to travel through a substance obviously makes a difference as to the amount absorbed. That's your path length. The longer your path length, the more your sample is going to absorb. So that's one factor that factors into that slope. Path length is a function of your instrument. And we'll talk about the instrument itself in a second. Different instruments are going to have different path lengths. So that's path length. Now let's look at absorptivity. Absorptivity I think is best explained, absorptivity is best described as a factor If you've had an art class, then you realize that different substances absorb different colors of light. Therefore, different substances are going to respond differently to different colors of light. Some are going to absorb a lot of them, some are going to absorb a little of them, depending on the wavelength. Absorptivity is the factor in the Beer's law formula that reflects how responsive a substance is to a particular wavelength. Therefore, absorptivity is going to be different for every single substance out there at every single wavelength, because absorptivity is different for every single substance out there, and because path length is different for varying instruments, in the laboratory we actually use Beer's law, as a graphical function. We actually in the laboratory use the A equals the slope times concentration form of Beer's law. Would you write down the word wine for me? Write down the word wine for me, W-I-N-E, wine. In the laboratory, if we have an unknown sample, so I have an unknown sample, I want to know the concentration of this sample. In order to use Beer's law, I have to know the identity of the substance. So I should point out right away, well, I don't have to know the identity of the substance. I take that back. There's a way to do it without knowing the identity, but that's beyond what we want to talk about right now. It helps if you know the identity of the substance. And you want to determine its concentration. So what we're talking about when we talk about Beer's laws, we're talking about a quantitative measure, or a quantitative technique. So we have a sample whose concentration we want to know. We would go to our instrument, and our instrument here would be a UV visible, in today's lab, a UV vis, ultraviolet visible spectrophotometer, and we'd place in our spectrophotometers a series of samples. These samples would have different concentrations. In other words, I'm going to make some standards. So I'm going to make some samples whose concentrations I know. In other words, these are what we refer to as chemists as standards. I would place these standards in my spectrophotometer and measure their absorbance. I would then plot a graph of the absorbance versus those standard concentrations. And I'd use that plot of absorbance versus concentration of those 4 standard samples I took to plot a line. If I have a line, I can determine the formula for the line of best fit. This would give me the relationship between absorbance and concentration. Then what I would do is I would take my unknown sample here, I would place my unknown sample in my instrument, I would measure its absorbance, and then use the formula for this line to determine the concentration of my unknown. The use of standards to draw this graph, it's what's known as calibration, or determining how an instrument responds to a different material, checking and making sure that the instrument is working right. This is an important, crucial job of a chemist. Matter of fact, if you've got a job in industry as an entry-level chemist with a bachelor's degree, one of your big jobs on a daily basis would be to calibrate an instrument, or at least run check standards to make sure that the calibration of the instrument was still valid. So as you can see, Beer's law is fairly simple. Matter of fact, Beer's law is so simple and so easy to use, even a biologist can do it. Matter of fact, the first time I actually used Beer's law wasn't in a chemistry lab, it was in one of my biology courses. It was the biologist was using it as an easy way to do cell counts rather than have to do that little microscope grid thing. They were measuring the absorbance of the cells to a function of light. So it's a very easy, very useful technique. UV visible spectrophotometers, like the ones you'll be using today in lab, are very rugged, durable, hard to break instruments. Not only that, they're fairly cheap as chemical instrumentation goes. You can get a very good one for less than $500. Therefore, they're used ubiquitously throughout industry. You will find them basically everywhere. Again, if you get a job as a chemist, it's going to be an instrument you should encounter. There is one problem with Beer's law. You'll notice when I initially drew that graph of absorbance versus concentration for you a little while ago, I drew it straight here and then a curve. There comes a point where the calibration of your instrument is lost. There is only what is known as a limited linear working range. When you are taking samples, because Beer's law varies or deviates because absorbance deviates from concentrations at high concentrations, when you're using Beer's law to measure concentrations, you always want to make sure that your unknown falls within your linear working range. I usually define the linear working range as the concentration of your unknown needs to be less the concentration of your unknown should be between the lowest standard you use to calibrate your instrument and the highest standard you use to calibrate your instrument. In other words, if we're really to report our the concentration of our unknown here in our little mock example with any degree of confidence, my unknown concentration, when I measure it, should be greater than 0.01 and less than 0.05. It should be between those two samples if I'm to have any degree of confidence in its concentration. But that linear working range is a very real thing when it comes to Beer's law, and we've actually had issues with it in lab working on this experiment. One last thing before I leave, why don't you write down bourbon? I wouldn't be a Kentuckian if I wasn't telling you to write down bourbon. Everybody write down bourbon.